Hi, my name is Aviv. I'll be one of the TAs here. I will be mainly responsible for the homework assignments. You can reach me at, first of all, Aviv R at CS. Okay. So welcome to the course. Like Chaim said, make sure you register with him. Okay, just make sure that he knows that you wish to participate in the course, because it affects the computational resources we'll be able to give you as part of the course. Later on, you'll see that you may need to use servers from the computer science faculty, which have powerful GPUs, and to gain access to that, you have to first register with us, and we need to add you to a specific student group so you can gain access. All right, so first of all, just a quick note about the course website. So we have a course website. You can reach it from the Vista Lab website on CS. You can go directly there. I don't know if you can read the URL, but basically it's I can write it down if you want. But this is the official website. All the course updates will be here. Okay, you'll see them here. We'll update everything, and all the material will also be here. Right now, we have lecture notes only for the next lecture, and I will put the slides up from today because they're very new. I'll put them up here soon, and also the tutorial you're going to see today will be here today or tomorrow. Yeah, sure. Okay, do you see it? It says Vista Lab Technion GitHub.io course number, CS course number. Okay. So please check here for updates. We will also email you if you're registered, but best to check here. Mainly, we'll email you to notify about updates here for the website. Okay. So let's begin with the actual tutorial. By sending Chaim Baskin, the guy that was here before me, send him your details, what faculty you're from, stuff like that. Okay. All right, so let's start. So this tutorial is very introductory. This course is going to be very applied. Okay, you're going to need to write a lot of code, get very hands-on during the assignments, and not everyone has a background with Python and Numpy, and specifically with the deep learning framework that you're going to use in this course, which is PyTorch. So this first tutorial will at least give you some introduction to Python and Numpy. What you see here is a Jupyter notebook. I'll explain what it does very soon. I hope that some of you at least do have experience with Python and NumPy and with Jupyter notebooks, but if not, then I will explain everything now. This kind of format is what we're going to use in some of the tutorials, and it's going to be widely used in the homework assignments. Okay, so the main goal of this specific tutorial is that after we finish here and you go home, what you're going to do is you're going to install the environment and the Jupyter notebook server on your own computer, and then you can run this notebook file for yourself and go through all the examples that you're going to see here. Just see that it works, that you managed to install it, that you iron out any kind of technical difficulties that you will encounter, obviously. It's very important to do this as soon as possible because the assignments, like I said, will be heavily based on this. Okay, so let's just start like very high level what we're going to see in this tutorial. So as I said, we're going to need Python. Python today is the leading language that's used for any kind of machine learning task. It has recently acquired many very important deep learning frameworks that are widely used in all the cutting edge research papers. The most as I'll say, it's very new on PyTorch, but it has emerged as the leading deep learning research framework. So we're gonna see that in the course, but it's not enough to just know that. You have to know a wide set of tools to actually do any coding, especially in our assignments. Okay, so basically I'm gonna show you some Python and NumPy basics. NumPy is like an extension for Python that gives you many kind of vector operations and linear algebra and stuff like that. That's, for example, that's built into MATLAB. So it kind of, if you take like Python and NumPy, you get a computational environment that allows mathematical computing. I put a link here for if you know MATLAB well, and you can go there. And there's like kind of a reference table that will help you. Okay, so what we're going to do in this tutorial is just quickly I'll explain how to set up your environment. I'll explain what the Jupyter notebook is, what you're looking at right now. And then we'll start going through basic examples in Python and NumPy. And we'll see if we manage to finish. We might not manage to finish because there's a lot of examples here that I put in, but the important thing is that you understand the concept and you're able to do this yourself. Go over the notebook, look at the examples and run them. Yes. Okay, yeah, good question. Both, both, because usually most of the things that you run won't be very heavy and computationally intensive. You can do it on your laptop, but once we get to training like large models, then we will need much stronger machines mainly with GPUs. So if you have a computer with an NVIDIA GPU, then great, you can do everything on your own hardware. But probably if you don't, then you will need some access to computational resources, which we will provide. And in that case, then you will probably train a model on those machines and then import the model to your laptop, and maybe we'll just do some inference on that and answer some questions. So I think you will be able to do most of it on your machine. And it's important that you yeah, it's a good idea. Okay, there are third-party services you can go. Like there are various kind of cloud environment that you can use instead of doing everything locally. But I'm gonna just show. It's very simple to do it locally. Okay, so basically we're using a package manager called Conda. I don't know if you come from a Python background, then you maybe know pip and friends. So virtual env. So Conda does the same thing. It basically installs Python and various third-party libraries in a contained environment on your computer, but it doesn't interfere with anything else you have installed. Okay, so so what you're gonna get? You're gonna get some kind of file called environment.yml. I'll show you the file. It defines any kind of dependencies that we have, and Conda just uses this file to install everything for you. And the environment includes Python and every other package that we're going to need. It's the same concept for the tutorials and for the homework. So hopefully, the goal of this is hopefully to reduce friction, and you don't need to install manually anything except Conda. Once you install Conda, then it will install everything for you based on a configuration file that we provide. So it should be pretty straightforward. Okay, so I provided links here. You can just follow them. Okay. I'll just show you like an example of running this. Maybe we should turn off the light. So is it large enough? Can you read it? Should be some kind of light here. Okay, so I'll just make it quick. So basically, if you follow the instructions there, after you install Conda, you need to follow the instructions for your own kind of platform. It's very simple, at least on Mac and Linux. Then I tried it. It was very simple. Basically, what you can see, I'll show you the example. You can see you get kind of a file like this that specifies a bunch of dependencies, including the specific Python version that we want, and a bunch of packages. And all you need to do really is run something like that. okay, and it will install everything for you. After it's installed, you can see your environments using Conda. You can see I'm using this is my current environment, CS number of course tutorials, okay, and it basically just installs it locally to my user. If I now say which Python, okay, you can see it's running the Python from this folder. And if I, for example, if I run some kind of Python program, then it will use this Python, including all the dependencies and stuff like that. So it should be. Yeah, if the environment is active, so active means that you see this kind of asterisk, and to activate it, I wrote here. So you run conda activate and name of environment. After you install everything, you just have an environment, you can run it. It will include everything that you need. Okay. So now what's Jupyter? Jupyter is a platform for interactive notebooks that contain code and prose, I don't know, markup text, okay? So what you're seeing here is a program called Jupyter Lab. It's a server running on my computer, and I open it with my browser. After I run it, okay, I'll show you again how I ran it. After you just run it, then it gives you a URL. Okay, I don't see the URL now, but well, you'll see in the terminal you just get a link and you can just open it. And I think it even opens the. Okay, here it is. After I ran Jupyter Lab, then I got kind of this nice URL. You can just copy it and open it in my browser. And what it does is basically run a web server on your laptop that hosts the Jupyter notebook server. So what does this server does? So what it does, you have basically two kinds of elements here in the notebook. You have code cells and markdown cells. So for example, this is a code cell. You can see this is a very small Python snippet. It computes the answer. Let me just sorry, I should have done that before. Just clear all outputs and run everything. Okay, so I just ran this kind of snippet live right now for you. What's happening is it's behind the scenes. It has a Python interpreter running in this environment, and it just lets the interpreter evaluate this code block. So it's really live. If you change anything here and rerun it, and you can see immediately the output just below. Okay, so this is very, 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 very useful, and you'll see like if you look at the course books and stuff like that, and many books in machine learning and deep learning specifically, most of the examples that you're going to get with the book are in this format of Jupyter notebooks that accompany the book. So it's very beneficial to anyway to use this stuff. Okay, and you can write text and in the markdown format, and you can even write equations in LaTeX. You can see here it renders the equation for you. And for example, this is like markdown. It's a markdown list. And when you run the block, it renders it nicely as a list. So that's the whole idea of the Jupyter notebooks. It's an environment that you can use to interactively work with code and text. So for example, in the homework assignments, I'm going to talk about this in the future tutorial, but you'll get a bunch of notebooks and a bunch of code, and you'll have to, in the notebooks, use the code, and you have to write your own implementations to augment the code that you received. And the notebooks will run everything for you and show you like outputs and graphs and stuff like that. So it doesn't just like show textual outputs. It's really interactive. You can really see plots and graphs and whatever. I'll explain everything. You'll submit all the outputs, basically all the outputs and the code. But it will be very automated. Yeah.
Do you recommend using Jupyter Lab instead of Python?
Oh, it's not instead of PyCharm. You use PyCharm to write the code. This is just like an environment for example, for this tutorial, just for me to show you examples. When you do the assignments, okay, if you need to write a bunch of code, you won't do it in your browser, okay? It's not convenient. Even though you can, for example, here I give you like a package, so you can see that you can edit this, and if you change it and then run it in the notebook, it will reload it live. But I'll talk about this later. But basically, what you're going to do is you're going to use any editor you want. You can use PyCharm, write your code, and the notebook will just run it for you and show you graphs. So it's like all the interactive stuff will be here, and you have to focus on the actual implementation. So that's the motivation. Any other questions about the technical stuff? Okay. So we have 2 sections here right now that we're going to go over. I have a basics of Python section and a Numpy section. So it's kind of long. There's a lot of examples here, but most of them are very, very easy and low level and basic programming. So if you programmed before, it's going to be very easy for you. Just show give you a flavor for the syntax in Python. And Numpy it's a little more advanced, but basically if you have at least some experience in any other kind of scientific computing like MATLAB, then it will be similar. And from here on, if you already know Python or Numpy, then this may be very boring for you. So you may want to, I don't know, consider not being here, but at least you should install everything like I said today, and then run it and go over the examples yourself later. Okay, so basically Python is very nice to look at. It has it's known for having a significant white space. So for example, this is like just a small example of a Python function showing some language features. Okay, you can see just a quicksort algorithm. Some of the things here are a little interesting. So what are these? What's this syntax kind of doing? Okay. So but basically, we're going to see it. It's called list comprehensions, and it's very intuitive. I think just looking at this right now, if you understand quicksort, then you pretty much understand what this is doing. Okay. So that's just like a taste. I'm going to really run over all the examples because I think you should be able to do it yourself. So how to structure your code. Basically, Python code is composed of packages and modules. A module is just a Python file. For example, this is a module. Okay. A Python module can contain any kind of Python code from functions to just like top level code, like the calling of the function and conditionals. This is run when you import the module, and the package is just a folder containing a bunch of modules. Almost there's like a technical detail with there's like a special file that says it's a module, but from recent versions of Python you don't really need that anyway. So basically you can think of it like it's written here. A package is a collection of modules within a directory, and you have many packages in the Python standard library, which means they come with Python, so you can just use them. This is how you import them. If you want to use math, like any kind of constant from there, you just import math, then you can use it. And you can also specifically import, for example, here I'm specifically importing a specific function from a specific module in a specific package. Okay, and here I'm gonna call it. Okay, here for example I used my math package and my sys package. Okay, so unless you specify a specific name, as you're going to see later with Numpy, you need to be very explicit about every object you use from the package. Okay, so this is like basic standard stuff. Okay. So as you can expect, Python has numbers. You can see these examples. Common number operations. Maybe exponentiation is a bit different from other languages. If they have it, then usually it's not like that, but this is the Python way. Okay, so I'm showing you more examples. Another interesting thing, Python has 2 kinds of division operators. So So this is integer division and this is regular division. Okay, as you can see here. If something is too fast or unclear, then just tell me because I'm gonna kind of run over all the examples. Okay. So Boolean operations, it's like kind of like you expect, except that it uses kind of keywords for that. Okay. Good. Working with strings, also like you expect. And the only really interesting thing here is to see is this kind of syntax. This is called an f-string literal. Okay, it's new in Python 3.6, which means it's pretty new. It's a very convenient way to output variables from your code. Probably you're going to use that when, I don't know, you write some models and need to debug them and you have lots of printing. This is a very convenient way. You can see I have two variables there, and I'm just embedding them in the string with these curly braces, and everything is printed nicely. And also you have kind of the more old way with the sprintf format. You can see you can get the same result with a much nicer syntax. Okay, so nothing here is very, very interesting. Python is also an object-oriented language, so any object you have, while you're working with it, it has instance methods that you can call. For example, strings have a bunch of methods that you can use to capitalize them and uppercase them and stuff like that. So you can explore. By the way, when you're using Jupyter notebooks, you have completion. So if you just you can use tab to get a bunch of methods from the object, and also shift tab for documentation built in. So it's pretty convenient that you can use also if you need to like explore stuff. And oh, another thing I wanted to tell you about Jupyter notebooks is that there's a built-in console. If you go to File and no, not File. What was that? Yeah, File. Okay, File, New Console for Notebook. Then you get a console here. Okay, this is an IPython console. It means you can type any Python commands into this, and also all the variables that are in the notebook right now, you can see them here. For example, if I say S, it says hello because S is defined. So I can use this for like exploratory coding. I can just try stuff out in the console, and then when it works, I can just code it here or code it in my actual code using an editor or stuff like that. Okay, so this is also very, very helpful. It kind of helps you work much faster, discover like functions and APIs and stuff like that. Okay. So nothing very interesting about numbers and strings. Lists are not very interesting also, but I guess as opposed to arrays from lower level languages, you can resize lists. So you can see these examples from, okay, so you create a list like with a bracket syntax. It's very simple, and you can use various kinds of indexing. For example, negative indexing. Okay, note that it's not like MATLAB. It's not one index. It's zero index. So the second index is actually the third element. Okay. Note that. You can change. You can put any kind of type in a list. Okay, and you can resize the list by finding more elements, and you can also make it smaller. Okay, all the examples clear. Okay, now slicing is a kind of syntax that allows you to get elements from lists. This is very useful. You'll see the same kind of ideas in the Numpy package when you work with tensors, and you need to get various kinds of dimensions from within the tensors. Then you can see the same kind of slicing ideas. So basically, what slicing does is just allow you to grab a bunch of elements. Note that everything is exclusive and zero indexed, okay? Everything, always. So if you see, for example, this kind of slice, okay, from 2 to 4, okay, you're specifying a bunch of indexes. So index 2 would be here, the third element, and index 4, okay, is exclusive. Okay, see that? Okay. So this is another simple slice from second index to the end, and up to second index, exclusive, everything. can specify up to the last. -1 means last. You can also do -2 and stuff like that. So it counts from the back of the list. Okay, you can also specify steps. So here the third slice is the step size. So you're going from index 0 to index 4 and jumping with a step size of 2. Okay, so this is from here, you jump to here, and then you're not including that. Okay, hope you can follow that. Again, if it's too fast, then I encourage you to do it yourself and actually play with the code and change stuff and see what happens. It's kind of nice. Here you can change a slice, and this is an example of removing elements from a list with 2 different ways. Okay, let's go over loops very, very quickly. There's a simple for loop that you can use. The same kind of syntax works for everything, lists and other kind of containers. You'll see later dictionaries and stuff like that. Dictionaries, sets, tuples, same kind of syntax always works. The for. If you need to get an index, you can use this function, enumerate, which gives you, for each element in the collection that you're going over, it provides you with a tuple of the index and the object from the collection. Okay, so you get that. Notice again the f-string interpolation part. You can put any kind of Python expression here in the brackets. So in this case, it's +1. Okay, list comprehensions. This is a very convenient way to transform a list into another kind of list. You saw that before in the quicksort example, where there was like 3 lines of kind of Python unique syntax. You can see, for example, here, this is a for loop based way to square some numbers. Okay, so you have to go over the numbers and square them, and then put the squared numbers in a new array, and then print the array. Okay. By the way, I didn't say another thing about Jupyter notebooks. The output that you see is the last expression. Okay, so if the last expression is a value, then you will see it printed, but it won't print any intermediate values, just the last one. So if you want intermediate stuff, you can either split the code cell or print it. Okay. I have a shortcut for that, but I just split it very badly. But it's in the, I think here, somewhere in the menus. Somewhere in the menus you can see. There's lots of stuff like merging, splitting, running all cells up to a certain point, clearing all outputs, restarting the kernel. I also didn't say that. I said there's an interpreter running here in the background and running your code cells. So that interpreter, it remembers your variables. Like if you define the variable, for example, nums, and then you keep running, then that variable is in memory. Okay, and then you can just run something else that was before that or back. You might like get in a different state than if you would run everything directly. So you can, for example, you can restart the kernel using this menu, and that just means that you're getting a new Python interpreter with all the variables cleared, and you can just run everything from scratch, which might be useful. Okay, so instead of this kind of a for loop, you can use something called a list comprehension, which will get you the same thing. It's basically like writing the whole thing in a single line and wrapping it with these kind of brackets. What it does is map one list to another list using an expression. So this expression it's like a lambda expression. Other functions in other languages, this will map every element in your array to a new element and then create a new array. So it's very, very useful. And you can also add conditions. So like that. You can just think about it like you take your for loops and just write them in one line. You can even nest them. Okay, so this is an example where it's like a for in a for, double for loop, and you can also do that, but that really isn't readable anyway, so maybe you don't want to do that. Okay, next up, dictionaries. You probably know them from other languages as either maps or hash tables or stuff like that. So very easy to define it. There's a literal for that. Okay, just define like a literal dictionary. You can see you map from keys to values, and the keys can be any kind of type, and the values can be also any kind of. No, the keys can't be any kind. They need to be an immutable kind of type. So they can't be a list, but they can be a tuple. You'll see that later. It can be a string, which is immutable. You can't put anything that's mutable in a key of the dictionary. Anyone remember why? By the way, why can't you put mutable stuff as keys? Yeah, exactly. Because the hash function will change if you mutate it, and then you won't get your actual element back if you try to. So yeah, that's not related to Python. It's true in all languages, I guess. So this is an example of setting entries, retrieving entries. If you try to get an entry that doesn't exist, you will get an error. An exception will be raised, but you can use these kinds of functions that have default values that will get you your defaults. Okay, you can use again for loops to iterate over dictionaries, as you can see here. Okay. You can also get a tuple of key value pairs with the items function from a dictionary and then iterate over that. Okay, and similar to list comprehensions, you can also do the same kind of thing with dictionaries. You see, the only difference is that you have this colon here that basically says I'm taking something and mapping it to a key and a value. So you can have like a mapper part, a mapper function, and a value function. And then you can just create a dictionary from a list or from another dictionary or whatever. Okay, sets. So sets are like a dictionary without the value. So I'm not gonna show that too much. Okay. Again, there's a comprehension syntax for that. So it's without the colon, but with curly braces instead of brackets. So similar to what you saw. Okay, tuples. These are like lists, but they're immutable. You can use them as keys in dictionaries. And they're very useful because you see them coming up in various places. For example, if you return multiple values from a function, then you actually return a tuple and you can unpack it. I'll show you just an example. So you can see you can use them similar to lists with all the kinds of indexing. And here you see that you can use it as a key in a dictionary, and also that you can unpack it. For example, here I have a tuple, and I'm assigning it to 3 variables. And then the last expression in the cell is 3 variables with commas, so it's creating another tuple, the notebook. But basically what I did is I unpacked the tuple to 3 elements. So if you return multiple values from your function, then basically you're getting that. So you need to make sure you unpack it if you want to use it as 3 different things. Okay, so functions, we saw previously how functions look like. Okay, this is the syntax for functions. You can also use kind of keyword arguments for optional things with default values. It's kind of, this is a very simple example, but the more general example is here. Okay, I think this might be a little. These examples will be a little hard to understand now, but if you play with the code, you'll get it. Basically, every function in Python has a bunch of arguments that are positional, which means they're required, and then you can include some extra positional arguments which are not required, and then you can have these keyword arguments which are key value pairs. Okay, you have to specify their default, and then you can also include some kind of extra arguments that you can pass in. Okay, so I'm showing you this because you're going to see it when you use documentation. Like you open the Numpy docs and the PyTorch docs. Many functions will have these kinds of star args and double star args. Okay, so just if you run this, you'll get it. You get how it works. So here are just some quick examples. Okay, so here we have 3 positionals and 3 keywords and all the extras. Okay, so you can see here. The first 3 are the positionals, and the other 3 are the extra positionals. Okay, when you write your own functions, by the way, you don't have to do any of that. This is just like the most general case that I could show. Okay, so there's various other kinds. For example, this example, then you use some kind of list, and then you pass all the elements from the list using this kind of syntax, which is kind of expanding the list into the positional arguments of the function. Okay, so if I run that, the function will say it got 1, 2, and 3 as the positionals and 4 as the extra positional. And then I can do something like that with the keywords, and then I get 3 positionals, no extra positionals, and the keywords that I specified. Note that I added an extra keyword that wasn't defined. Okay, so I got it here in the extra keywords. Okay, and here's another case which you can take a dictionary and then use the double star syntax to expand the dictionary into the keywords of the function. Okay, so these are very useful tricks because they're not really tricks, and you'll see them kind of in many functions in the Python API and also in the libraries that you're going to use. And here is an example. If you call the function with not enough positionals, then obviously you get an error. So it's very flexible, but you need to at least specify some kind of minimum. Okay. So we don't have a lot of time. Let's do classes quick. So classes have all the features from other object-oriented languages. They have instance methods, instance variables, state that you can use. For example, here is a very simple class. It has one state variable, okay, and has one instance method. It's the same method that you saw before, and then you can create a new class just by calling it like that. This method is a special method, the init with double underscores that will be which will be run when you construct your class. Okay, so. Now, a few more words about these special functions with underscores in Python. They're called magic functions or magic methods. What they allow you to do is kind of integrate Python into your own code. For example, here I'm creating my own collection that I can then use a for loop in Python to go over its elements. So to do that, what I need to do is implement basically the len and iter magic functions. You can just if you read the code, and it will be very simple. You don't replace because here it's just I'm not extending anything, not extending any class. I'm just if I create a special function with this name, and then I use and then I create this instance and I put it in a for loop. And what the for loop will do is it will check whether my object implemented the iter method. If so, it will call it and get an iterator. And on the iterator object, it will call the next function to get the next element for the next iteration. Okay, so this is an example. Also, len. If you implement len, then you can use this. Okay, you can just use the len function on your own. And there's many other. You can this way you can override like operators like less than, greater than, other math operators. You can do various interesting things. And also, you see this a lot with when you see Python code and you look at, you'll see many of these kinds of functions, and now you can understand what they're doing. That their purpose is to give this class some abilities with the actual Python. Okay, so we finished with the Python section. Are there any questions about that? Okay. Like I said, I really encourage you to play with the examples, create your own examples. It's very easy. You don't even need this specific notebook. There's lots of resources online, but this is a good place to start because you already saw these examples. Okay, so Numpy, as I said, it's a scientific computing library. It provides you with tensors, which are n-dimensional arrays, highly useful, and it's very useful to know this because many libraries use NumPy arrays as like a basic data type. Even when you want to create graphs and you use a graphing library called matplotlib, which is very common, then all the kind of x data, y data, and things that you will pass it are NumPy arrays. So you kind of need to know it. And also you'll see that the PyTorch tensors have very similar kind of conventions and syntax than NumPy. So when you know NumPy, you really know almost everything you need to know. The difference is that PyTorch tensors allow you to run on GPU, do operations on GPU seamlessly, and NumPy does not. Okay, so this is how you import NumPy. Once it's installed in your environment using Conda, as we saw before, this statement should work. If this doesn't work, then you didn't install it or you're not in the correct environment. Okay, you need to Conda activate your environment. All right, so like I said, a NumPy array is an n-dimensional array with values of the same type, and You have two basic important properties that that I will show you, and you constantly check for: the rank, which is the number of dimensions, and the shape of the array, which is a tuple of integers giving the size of the array along each dimension. Okay, so let's see some very simple examples. So here's a rank 1 array A. Okay, you can see its shape is a tuple of one element, 3. Okay, this means that it's a rank 1 array. Now, in MATLAB, I don't think this really exists. In MATLAB, you either have column vectors or row vectors. You don't have exactly this kind of thing. These rank 1 arrays, I'll show you an example soon, can be thought of as both. If it was, if the shape was 3, 1, okay, then it would be a column vector. If it was 1, 3, then it's a row vector. But if it's just 3, then it's neither of those. Okay, and you need to kind of make sure, because sometimes you'll get strange errors about shape mismatches, and it might be because of this kind of stuff, that you're using a rank 1 array where you shouldn't, or you should. Sometimes you should. Okay, so this is a rank 2 array, which is a matrix, regular matrix. You can see how beautiful the matrix is, and it has a nice shape. Okay, 2 rows, 3 columns. You can use indexing like in Python. Okay, and you have many functions. This is a small sample. It's kind of similar to the MATLAB function, zeros, ones, stuff like that. You specify a shape and you get an array of that shape. Okay, so here's a few examples. Identity function. You can also specify a data type. So this is an int and the array, and this is a float and the array, for example. Okay, so like I said, rank 1 arrays are kind of strange. You can treat them both as columns and as row vectors. Here's an example. I have a rank 1 array here. Okay, let's run this. And I'll create also a column and a row from it just by running reshape. Again, similar to MATLAB. Only difference is this -1 syntax here in the reshape. So as you can guess, it means, it also says, it's kind of like figure it out. So figure the number of rows out, and I want 1 column. So I get a column, and here's figure the number of columns out, and I want 1 row. So I get, here's a column, and here's a row. Notice the row has 2 brackets, okay? Because it has 2 dimensions, whereas this has 1 dimension. Okay, so it's 1 array, and this is like an array of arrays, but it's an array of 1 array. Okay, so kind of easy to see that when you look at the brackets. Again, it's not exactly like MATLAB. Okay, so here are some examples that are using it. So here I'm computing vector or vector matrix products. So this is NP dot is kind of a versatile function, which depends if you give it 2 vectors or 2 matrices. It's kind of trying to do the right thing. But here are some examples that you can play with and see what happens. Basically, you can see that when I multiply 2 rank 1 arrays with dot, okay, this is the output. It's not. Don't use the star operator because it's element-wise. I'll show you that. Okay, so you get what you expect. The dot product of 2 vectors, but you can see here the differences in the dimensions. Okay, so this is a rank 2, and this is a scalar rank 0, and this is a rank 1. Okay, so I really encourage you to try it. And here you can see column. When you use column and row, you get the same result, but it's now rank 2. Okay, and if you do column and row, okay, then you get a matrix with the same function, always using dot. So these examples are kind of interesting. I'm not showing every example here because if you combine it wrong, then you will get an error about shapes. Okay, so some kind of indexing. So again, slicing, we saw that for Python lists, same for Numpy arrays. Okay, but now you have more dimensions. So there's kind of various things you need to watch out for. So here I'm creating an array, a matrix, 3 by 4. And I'm just showing how to slice it. For example, here it takes up to row 2, up to row with index 2, okay? So it's the first, because this is index 2, okay? So it's row 0 and row 1, and from element 1 to 3. Okay, so It's this middle part. Okay. Hope it's clear what the output here. Why this is the output. Okay. If it's not clear, ask or run it yourself. Also at home, because you can try various things. An interesting property is a slice is a view. So you basically, it's showing you the same kind of memory, the same kind of data in memory. So if you change something, here I created a slice. So B looks like a 2 by 2. But if I change something in B and then show you A, you will see that A is also modified. Okay, so it's a view. It's not copy. If you want to create a copy, you create another array. You just create a new ND array and pass the old ND array, and it will create a copy. But if you just slice, then you're not creating copies. Also, when you reshape, transpose, stuff like that, you're not creating any copies. Okay, so these are examples, also kind of tricky, different from MATLAB here. Here I have a matrix, okay, and I'm doing different kinds of indexing here. You can see I'm always taking all the columns. Okay, but here I'm taking the index 1 row, and here I'm taking basically the same thing because it's excluding the 2, but I'm getting a different shape. Okay, so if I specify an integer for an index, I will get a lower rank. And if I specify a slice, then I will get the same rank 2. Okay, so you can see here, this is rank 1, this is 4, and this is a row. This is a row. Okay, so it's a 1, 4. So again, it's a little different from MATLAB, but it's useful. What else is there? Okay, so this is another indexing example. Not very interesting. I'll skip it. Okay, so I'll skip it. This is very, very, very simple. Just you create pairs of indexes, and you get any elements you want from the array. Boolean indexing is similar to MATLAB's logical indexing. So you can say I have an index that's all the elements of an array where the array is larger than 2. Okay, and then you can say array at that index, or you can just say, you can put it also here, like A larger than 2. And it's the same. Okay, so again, very similar to MATLAB in this regard. Okay, there's lots more stuff about slicing. You can see here that Numpy automatically selects data type for you if you have, if you specify. This is a Python list, a regular Python list, and you provide it to the array constructor. So it's a list with only ints. So it guesses that you want to work with ints, and here it will guess that you want to work with floats, and here you specify explicitly what data type you want. Okay. So another source of errors, various errors when you're plotting or training or stuff like that, that you're working with different kind of data types. You have, for example, a float and or a float 32 and a float 64, stuff like that. You might get errors because of that. So all you need to do is just create a new array with the right data type. Also, you can arrays have functions that convert them to another data type, returning a new array with that data type. Okay, so now something that I mentioned before, that all the operators are element-wise when you work with NumPy. For example, here you can see various kind of examples when you take two arrays and you do element-wise operations, x plus y or np add x, y. This is two kind of different syntaxes for the same thing. Even, and this is what I actually wanted to show, even when you use this kind of product syntax, it means element-wise. It does not mean kind of a matrix or matrix vector thing like it would in MATLAB. It's not like that. It's element-wise. Okay, if you want matrix vector, stuff like that, then you need to use other functions. Like I showed before, I showed the dot function, and there are some others, but dot is usually what you'll use. Okay. So okay, this is what I just said. So here are some examples quickly. You can see here two vectors, and you dot them. So notice that they're rank 1, okay, but you can still compute an inner product, even though it's not clear if they're row or column, because they're both, and it will do the right thing. Some more examples of using dots. So I'm just giving you some examples here of matrix vector and matrix matrix. You can just go over that. I really suggest that you do. Okay, the last kind of thing that's important is broadcasting. So I'll just mention it because we're kind of running out of time. I want to explain this, why it's important, and again, I really encourage you to try it out and also read. I linked here to the documentation for that. It's kind of easy to get confused by that, so you need to read it. What the purpose of broadcasting is to basically allow you to work with arrays of different shapes and not have to write any explicit loops. Okay, you can for example take a matrix and like a rank one vector, and we want to add that vector to all the columns of the matrix. So it's called broadcasting because it figures out how to duplicate your data to fit some kind of other data. For example, you have a rank 1 vector, you want to duplicate it and add it to a matrix. So there are kinds of rules how it's done, and you need to be aware of them because it really allows you to write highly efficient code. If you do that, instead of writing for loops, and you can vectorize your code. You can basically write with one line something that has the loops behind the scenes implemented in C or Fortran or whatever Numpy actually uses, because it's using very efficient computational libraries behind the scenes. So you can see here an example. So basically, I'm not gonna. I guess I don't have enough time to go into it now, but these examples show you like the regular way how you would do it. You want to add a vector to a matrix. You would create from that vector, replicate it, and create another matrix, and then add them. So here's with the for loop, and here is with np-tile, which replicates your vector. And basically, what you could have done is just that. And because behind the scenes, all these regular operators, they do the broadcasting thing. They do the broadcasting, and you need to be aware of the rules, like how two vectors are broadcast together. So I don't know if I should go into that. Okay, yeah, I wrote it down here, the rules, and I linked to the documentation. The gist of it is when you have something like this, like these shapes here, okay? So you have a matrix, okay, and you have a rank one whatever. It basically replicates it for you because this is for example, I don't know, 3 by 3, so the shape is 3, 3. And here you have a rank 1 array. It will automatically understand that you can replicate this to that size because it's compatible at least on some dimensions. Okay, if this was like 3.1, then you can see it's compatible in this dimension. All you need to do is take the dimension with the 1 and replicate it 3 times. Okay, and when it's missing a dimension, like it's rank 1, like it's that shape, then the rules say that you prepend the 1 dimensions. Like you think about that, you take a rank 1 array and put it just in more brackets, okay? It just puts more nested arrays. So you get from that, you get that, okay? And then you do your operation. So that's what's written here in these four rules. And if you read that and follow the examples, then you kind of understand it. So it's a really important concept. In PyTorch, all the tensors actually implement all the same kind of broadcasting semantics. So if you understand how to do broadcasting and write vectorized code with Numpy, it will be exactly the same when you do it in PyTorch. Like I said, only difference is PyTorch allows you to run your computations on GPUs, but the semantics will be the same. Okay. So I really encourage you to run through these examples. And that's it, unless you have any questions.